I want to begin by showing you what are the opportunities that we have in observing binary black holes. I'll start with that, both from ground and underground in space. Then we want to talk about what we know about binary black holes. We already had a talk by Sathyaprakash on numerical relativity simulations, so I won't really mention much except to say what are the interesting properties that help us detect them and understand them. I'll then go on to talk about what are the current status of observations in terms of not detecting any binary black holes directly. What's the status and what do we hope to learn in the near future? And finally, I will mention what future observations of gravitational waves will tell us about black holes and binary black holes both. The parameter space that we are looking at is pretty huge. This plot is a plot of the frequency, dynamical frequency of a gravitational wave source as a function of mass. It's 12 orders of magnitude both in mass and frequency. And there are a number of curves, and I would like to slowly go through each one of them because that might basically be the summary of the talk. On the one hand, we have a region here which says no radiation expected. That's based on current numerical relativity simulations, which say when binary black holes merge, then there is some amount of radiation that goes into quasi-normal modes, but probably not a lot of higher order modes are excited. So the dominant mode is the so-called 2-2 mode, which is indicated by this red dashed line, and then you have 3-3 mode, 4-4 mode, and so on. But there's not a lot of energy that's put into modes higher than 2-2, unless systems are very asymmetric, in which case anyway the total amount of gravitational waves that we can expect is already quite small. So in generically speaking, we probably don't expect radiation in this region if general relativity is true, and if anything is observed in that region, that means there's something wrong. We have to revise our understanding. In addition to that, there is this green line here, which is the last stable orbit mentioned a couple of times in the last talk. And that's an important landmark because gravitational waves, even though are emitted as a system evolves from whatever point here up to merger, most of the radiation comes from regions beyond the last stable orbit, and that's the reason why it is important to model them in that region. So I will show you in a minute how the luminosity depends on that region. And there are several dotted curves. These dotted curves, if a binary black hole starts off from that dotted curve, just as this intermediate mass of binary black hole, that would take 3 years to merge. But if it starts from one of these other dotted black holes, it might take about 1 day to merge. But if the system is heavier, starting from a much lower frequency, it would still take several years to merge. So those are those different dotted lines, what they mean. There is another important line here, boundary, which gives you the region that separates systems for which we can measure the change in frequency during an observational period from the region where we cannot measure. So any binary system that is located only in this region, we can't measure the change in frequency. But it's very important to measure the change in frequency because it's only for such systems that we can extract the physical parameters of the system, measure its mass, its spins, location, and so on. And therefore, while black holes in this region can exist, they are not very interesting from an astrophysical point of view because we can't really learn much about those systems. So these bands, the two white bands and this brown band are really the regions of interest. That's further divided into ground, which is a frequency from 1 Hz to about 10 kilohertz. Space, which is from a few times 10 to the minus 5 Hz to all the way to 1 Hz. And pulsar timing array, which is this region. I'll come back to these regions in a minute, But let's take a look at what the system is going to do, starting from something like R equal to 100 M. That's quite a large separation, but as you can see from this plot, the amount of time that is spent by different systems. If it is stellar mass black hole, it's going to spend very little time until merger. So that's what the track left behind a system is going to look like. Whereas a supermassive black hole starting from R equal to 100 M might spend several years in band. So, but the important thing is, what is the luminosity of gravitational waves in this, as they evolve from one point to another, and that showed as a sketch in this color plot. The luminosity increases as you go from black to red here, and most of the energy is really coming from this region here, after which of course the two black holes are merged and there's quasi-normal mode and the system vanishes. So because of the fact that you have most of the energy coming here, it's important to model the late time evolution of binary black holes, and that's where a lot of energy, both in analytical and numerical utility, have gone. So understanding binary black holes is very important. I'm not going to talk too much about the theory or numerical simulations, but I want to discuss some of the properties that binary black hole signals have and how we might be able to measure the progenitor properties from those signals. So binary black hole dynamics is characterized by a slow adiabatic in spiral phase, and in this region we can actually use post-Newtonian approximation to describe. And as you heard earlier, we know post-Newtonian approximation to a pretty good accuracy. V by c to the power of 7 beyond, when it is just dissipative dynamics, beyond the Newtonian approximation. But in this region where the merger of the two black holes take place, we need numerical relativity solutions to Einstein's equation. They are very difficult to model, but there are phenomenological models as well as extensions of post-Newtonian approximations called effective one-body model that is used in order to describe this phase. So it's not completely hopeless, but availability of numerical simulations is absolutely critical to develop those analytical models. And finally, we have perturbation theory to guide us. What happens when you have a highly deformed single black hole towards the end, and that leads to quasi-normal mode radiation. So this is the basic structure, as we all know. But then what do we need to measure in an experiment to finally understand what binary black holes are and put Einstein's theory to test? We need to measure basically 16 physical parameters, and these are characterized as dynamical parameters, which consist of masses and spins and eccentricity of the orbit. There are 7 of them, or 8 of them. And then there are kinematical parameters, which consist of the distance to the source and its angular parameters describing its position on the sky. But also the polarization and the orientation of the source given by the orbital angular momentum vector. So those are the kinematical parameters, but in addition to that, there is simply the epoch of merger and the signal space at that epoch, which we need to take into account in a search. So those are the parameters that we need to extract, and the signal shape plays a very big role in extracting them. And we can measure them with a single detector like ELISA if the signal is in band for a very long time, like a period of a year or larger. Otherwise, we need a network of detectors for a transient signal, as would be the case for Earth-based detectors. So how do we measure these physical parameters? It's done by using match filtering. And match filtering is very sensitive to the phasing of the signal, and the signal shape and phase is critically determined by the mass ratio of the binary, the spins, eccentricity, polarization, and the inclination. So those parameters determine the phase and shape evolution. Whereas the signal's amplitude and arrival times also depend on some of these parameters, like direction, polarization, inclination, and masses, of course, I left that. But it also is determined by distance and direction. So combining these two, we will be able to, and using match filtering, we'll be able to extract all the physical parameters as well as incidental parameters like direction to the source, etc., from gravitational wave observations. Not only is the in-spiral part of the binary evolution very interesting, so also the post-merger signal could be potentially important because it could even tell you about what the progenitor binary was even without observing the in-spiral part of the signal. So this diagram shows you examples of how that post-merger signal might look like if you include higher order modes. It doesn't really look like just a damped sinusoid. It is distorted because of the presence of higher order modes. And you see here the signal to noise ratio integrand as a function of frequency, which for some masses, like 5 times 10 to the 5, 5 times 10 to the 5 in LISA, the dominant mode is only the 2-2 mode, but when you go to higher masses like 10 to the 6, 10 to the 7, the observed dominant mode might actually be the 3-3 or 4-4, depending on what the masses are. So this is like really black hole spectroscopy. There are so many different lines that are present. You can think of these as lines that are present in the spectrum. You can, by studying them, derive properties of the black holes and even test generality. Coming back to this diagram, as I mentioned earlier, the opportunities for observing in the different windows, the ground-based detectors will essentially observe stellar mass black holes. So that region here is mostly stellar mass black holes, maybe intermediate mass black holes. When you go to the highest, the lowest frequency and highest masses will be around 10 to the 4 solar mass. The space-based detector here will be targeting supermassive black holes, intermediate mass black holes, and we have a big gap in observation there. We won't be able to observe, that's in the frequency gap, but pulsar timing array should be able to observe very large black holes that exist at the centers of galactic nuclei and merge and emit gravitational waves. So I will start off then by showing you the full spectrum of gravitational waves. There are many different sources and they cover the entire frequency band all the way from the inverse of the Hubble time to kilohertz range. So that's nearly 20 orders of magnitude in frequency range. And there are many interesting sources. Of all these, I mean, the 3 bands that are available to us, the pulsar timing array and the space band consisting of space detectors like LISA or the Big Bang Observer and ground-based detectors can target different sources. So let's start with the so-called very low frequency, which consists of observation of gravitational waves by using pulsar timing arrays. What these detectors do, they are detectors that monitor arrival times of pulsars, a bunch of millisecond pulsars. And by monitoring their arrival times and looking for correlations in arrival times, they are able to detect gravitational waves that pass by the Earth. That's a very simple cartoon. In the next talk, you will hear more about how that actually works. These pulsar timing arrays use observation of pulsars using radio telescopes. I've given a number of examples here. Currently, there are 3 different efforts, one in Australia, Fox pulsar timing array, secondly in Europe, European pulsar timing array, and North American nanohertz gravitational wave observatory. These radio telescopes have already begun to make a big impact, and I'll show you one recent result that's coming out of it, and they will soon be putting their data together to form international pulsar timing array, about which you will hear a little more. Their main target is to look at gravitational wave background produced by merging black holes throughout the universe. And if the frequency is in the right spot, which is in the nanohertz, or tens of nanohertz range, they will be sensitive. So a population of binary black hole mergers would produce a stochastic background that would be detectable by pulsar timing arrays. That's the basic idea. And the most recent results coming out of these observations are plotted here. Firstly, this is the prediction of what you expect for amplitude of gravitational waves as observed by pulsar timing array for different models, merger models of black holes in the universe. And this one here is some sense averaged. The black curve is an average behavior. The characteristic amplitude of hc equal to 2 times 10 to the minus 15, which would be somewhere here, will correspond to an omega of 2 times 10 to the minus 10. So what's the status of observations? This is the model, this is what the model predicts, and this is the paper. The European pulsar timing array has already set a limit and ruled out, let's say, extreme models. Nobody's surprised about that. But the most recent result, which is still unpublished, and my thanks to Shannon Call and Dick Manchester for providing the data point, the pulsar timing array from Parkes has already ruled out models to the right of this in some sense. So really we are getting very close. When the pulsar timing arrays pull their data together and begin to set upper limits or make observations, they could be at this level here. So within a few years, or maybe few years, maybe tens of years, with 20 pulsars and 100 nanosecond pulsar accuracy, you should be able to even surpass that mode of the distribution of expected binary merger model. So this is really getting tight, and therefore we expect over the next 5 to 10 years, pulsar timing arrays to make detections of gravitational waves. In the future, there will be other opportunities like the SKA, which will have even better sensitivity, and the field is extremely bright in this part of the frequency band. Moving on to slightly higher frequencies, but still called low frequency, is about 10 microhertz to all the way to 1 hertz, where we need to go to space in order to observe. And for a long time, we were thinking about laser interferometer space antenna, but more recently, we are talking about the ELISA survey mission, which is a white paper that has been submitted recently. And I want to just talk to you about what this ELISA mission can actually observe. For those of you interested, there's an archived version of that white paper that gives you all the details. So the concept here is to have a mother spacecraft and 2 daughter spacecraft in heliocentric orbit around the Earth, as shown in this diagram here. As they go around, the proof masses inside are simply going around the sun purely due to the gravitational dynamics, and there is no need to control them or to steer them. They follow this heliocentric orbit, and they follow a cartwheel motion as they go around, inducing a signal modulation in whatever is observed in gravitational waves. And this triangle, of course, rotates like a cartwheel, as I said, and that's important for some of the measurements that we make. The most important source of observation for these space-based detectors are really supermassive black holes again. We know that supermassive black holes exist in all sorts of masses, starting from millions of solar masses to billions or tens of billions of solar mass black holes. And one model that's put forward is that either they form as small black holes which grew in size as time went on, or maybe they were already giant sizes like 10 to the 4, 10 to the 5 solar masses and grew by simply mergers, black hole mergers, as shown in the simulation of galaxy mergers, which accompany finally black hole mergers within a Hubble time. So if this is true, then LISA should observe this population, the foreground population, and the signal to noise ratio expected is phenomenal. What this plot shows you is the visibility of supermassive binary black holes in ELISA as a function of solar mass, mass of the black hole, log mass of the black hole. This shows you how at different redshifts the signal to noise ratio will be quite large. So for instance, let's take a 10 to the 6 solar mass black hole, which can be observed all the way to redshift of 20. And if you do have hierarchical growth of small black holes like 10 to the 5, 10 to the 6, then they should be visible to the edge of the universe. They simply can't hide from ELISA. And that's true for quite a wide range of masses, starting from something like 10 to the 4 to 10 to the 8. So, of course, if you move away from this, you can't see quite all the way to redshift of 20, but quite a significant fraction of the redshift can be seen. Now, not only can we see these objects to high redshifts, but we can also measure them pretty well, as shown in this slide. Namely, masses can be measured to an accuracy of 0.1% to 1%. And that is very important because you want to know what the intrinsic masses of these big black holes are, because that is critical to testing the models of binary black holes. So in this case, black holes merging at z equal to 1. This shows you as a function of mass ratio and masses the signal to noise ratio that you can achieve, and this shows you the signal to noise ratio that is achieved at z equal to 4. And from those, it's pretty obvious. I mean, look at the numbers here, thousands and hundreds, which means that you can measure these quantities extremely well. In addition to big black holes going around each other, we can have small black holes going around a large black hole, and that produces a very complicated, very interesting signal in which there's a lot of modulation of the waveform as you have this spin orbit coupling which tilts the orbits, and very interesting signal. There is a dedicated talk by Leo Barak who will tell you how you will be able to measure the Kerr space-time nature by looking at the gravitational wave signal emitted by this small black hole as it falls into the big black hole. I won't say much more about it. Focusing on the high frequency, which is where I'll spend the next remaining period of my talk. This is the audio band. We can literally hear gravitational waves in this region. And there are many detectors that are already either built or under construction. American LIGO Observatory consists of 2 detectors at Hanford and Livingston. In fact, a third detector, which was in the same beam tube in Hanford, is now currently being shifted to India, which I'll talk to you in a minute. In addition to the 2 American detectors, the other large-scale detector that's already in operation is the French-Italian Virgo. British-German GEO 600 is a 600-meter interferometric detector, which is currently taking data when other detectors, the 3 big detectors being upgraded. This is an extremely important exercise for us because if there is a nearby supernova or if there is a nearby black hole or neutron star merger, we will be in a position to detect them. They have to be very close. And recently, we did have instances where gamma ray astronomers were very eager to find out when a gamma ray burst took place nearby, whether we had any gravitational wave data. So GEO 600, which is a British-German collaboration with a detector in Hanover, is an extremely important detector in this period. Japan is building a detector underground in Kamioka mines called Kagra. That would be using 3rd generation technology already to build a 2nd generation sensitivity detector. In some sense, because of the fact that you have to win over some of the noises, you have to go underground. But this is already, Japan is already making a big breakthrough here. In addition to that, we expect one of these, as I mentioned already, Hanford detectors to be moved to India. which will give a wonderful baseline to the worldwide network. Between 2006 and 2010, these larger detectors, Hanford, Livingston, and Virgo detectors took data, about 2 years worth of it, at really sensitivity levels not seen in this time until now. No detections have been made, but they are beginning to impact astrophysics, as I will talk about, but I will only focus mostly on black hole binaries, except with one exception. The searches that we do can be, for compact binaries, can be classified into what are called low mass binary searches and high mass binary searches and intermediate mass black hole binary searches. The low mass binary searches consists of searching for neutron star binaries mostly, but they may also include binary black holes. The merger phase of the signal here is out of the detector band, therefore we don't need to worry about including the merger phase. That means we don't need numerical relativity simulations. We can just use post-Newtonian waveforms to look at these signals. The search in this case is a two-dimensional space of search consisting of the two component masses, and we vary the component masses between 1 and 24 solar masses, and the total mass between 2 and 25, and we just use a match filter search. So the result is that we have the inspired horizon distance in megaparsec as a function of total mass to something like a few tenths of megaparsec for binary neutron stars. They live in this region of the parameter space, total mass. So for that, we have tenths of megaparsec distance, depending on which search you are looking at. This S6 is the 6th science run, S5 is the 5th science run. So you can see the improvement in sensitivity as we go from one science run to another. And different detectors have slightly different sensitivities. That's the LIGO Livingston detector, slightly lower sensitivity compared to Hanford. And Virgo detectors here, they start a little late, therefore this VSR1 is Virgo science run 1, 2, 3. So it's about tenths of megaparsec for neutron star binaries. For binary black holes, it's considerably larger. It could lead to hundreds of megaparsec as you go to higher ones. So what's the result? Well, we had an event which came to be known as a big dog event. What's plotted here is to show you convincingly that we detected this event and what it is all about. This is the cumulative rate of events. That is, as we pass the data through our analysis pipeline, we set a threshold that is low enough that we do keep recording events. They may not be much significant. So at lower values of the threshold, we have a large number of events. There are two types of dots here. The events in blue are the events that we actually get out of our detector. The one in black is an estimate of our background. I won't tell you how we measure our background unless you ask me the question time. So what we see is that when we have low thresholds, the background and the foreground are no different. So we can't really tell whether any of these events are true events or not. At very high signal-to-noise ratios, this background is falling off very fast, but we did detect an event that is significantly above, and if you ask how significant, it turns out that it's about once in 7,000 years that this event is mimicked by pure norms. So that's as significant as that. So we were about to publish this result, but it turned out that this event is actually generated by a signal that was injected in hardware by our experimentalists in order to test the pipelines, which is agreed beforehand, just that data analysts wouldn't know where or when or what parameters it would agree. So making that detection was extremely useful exercise in terms of both testing our pipeline, but also giving us great confidence as a collaboration that we are able to detect such systems. So since there were no real signals, what you could do is to set an upper limit on the rate, and the rate upper limit that we can set depends on the mass of the binary, because the greater the mass, as you saw, greater the distance up to which we can see. That means our heavier systems can be constrained better in terms of rate. So the rate here goes from 10 to the minus 4, minus 5, minus 6 per megaparsec cube per year. So for binary neutron stars, it's at the level of 10 to the minus 4 megaparsec cube per year, whereas for the heavier systems, it's about an order of magnitude of that. The gray ones are our S5 result, and the black ones are the results from the 6th science one. How does that compare with what we expect from astrophysical observations for detections? This slide shows that, again, this rate estimate per megaparsec cube per year, 10 to the minus 4 for binary neutron stars, and we are at the level of 10 to the minus 6 for the mode of the distribution that predicts gravitational wave observations to be routinely made. If that's the level, then we are about 2 orders of magnitude away, but the improvement in sensitivity by a factor of 10 will improve that level by a factor of 1,000. And this is the reason why there is such an excitement that these sources, which we know exist out there, will become detectable once we operate advanced detectors at their design sensitivities. So that's the expectation. These other two, really, we don't know whether they exist at all. And expected rates really come from the so-called population synthesis models, and a lot of things go into that. And by observing in this parameter space, we should be able to constrain astrophysics, and that's the goal, and also to, of course, observe if those systems exist for both neutron star black hole and black hole binaries. Particularly interesting is this region here. We are extremely close. In fact, if we improve our data analysis pipelines by only a tiny bit, we begin to rule out the most extreme models, and we are currently in the process of making our analysis pipelines better. Binary black hole searches, which is the second type of search that we do, now the merger part of the signal and the numerical simulations become very important. They are now incorporated in our searches. The search is still two-dimensional, but we do use spinning binary black holes in order to better understand our upper limits and so on. The heavier binary here either consists of a neutron star or black hole, but the range here is to take component masses from 1 to 99 solar masses and total mass from 25 to 100 solar masses. So it is complementary to the previous search that you saw. The sensitivity distance here already starts from hundreds of megaparsec because we are dealing with heavier systems, and goes to about 250 megaparsec for either spin equal to 0, in this case the spin is 0, or you could have positive spin, in which case the distance reached will be higher, or negative spin, in which case, either aligned spins or anti-aligned with respect to the orbital angular momentum. That's what I mean by chi less than 0. So in this case too, there were no detections, and we went on to set upper limits. The merger rate limit here is per megaparsec cube per million years, and instead of just year, this is a million year already. That means the numbers here are already 10 to the minus 6, and some of these numbers have really come very, very close to where we begin to make observations. In addition to stellar mass binary black holes, we also look for intermediate mass black holes. This search does not have to use any match filtering because the signals really last for very little time in our detector band. So we can use a burst search algorithm. We really don't use any sort of sophisticated match filtering in this case. We don't know really whether these exist in the universe, let alone intermediate mass binary black holes. We don't even know whether intermediate mass black holes exist. But some of the ultra-luminous X-ray sources are believed to be progenitors of these, are believed to be intermediate mass black holes, and there is therefore great interest as to what we can learn about them in this gravitational wave observations. They typically last, as I said earlier, very little in our band, 1 second or less, and they're tested using burst. So the upper limit in this case, the effective range, first of all, is at best about 250 megaparsec in this region of the parameter space. If we had used batch filtering, these could probably be a factor of 2 larger, but it used a burst search, so it is similar to what you saw in the previous case. And the upper limits, which depend on the masses, now are per megaparsec cube per million year, as in the previous slide. And the range anywhere between something like 0.1 to about 15, 20, or 50, depending on the different regions of the parameter space. This may or may not be very interesting, but you can see this is already at a level which is better than what we can do for stellar mass black holes. I want to finally talk about advanced detectors over the next 10 years or so, 2015 to 25. We will have a global network of detectors, Hanford, Livingston, Virgo, India, and Japan. These are the big detectors. These are the detectors with kilometer baseline sensitivity. And such a network is important in order to fully resolve the sky, measure its polarization, gets the angular position, and so on. This shows the sensitivity evolution. Strain sensitivity per root hertz as a function of frequency will improve by up to an order of magnitude, but more importantly, the bandwidth will improve significantly over a period of 10 years or so. That means that as a function of time, 2015 to something like 2022 plus, this shows the run durations that we expect currently, few months to begin with, but to go on, we'll go on to run detectors for years. And the number of detections that is expected is uncertain. And that's mainly because the rate itself is very uncertain. But I think it's over the period of 2017 to 18, over a year and a half, we expect the median predicted detections to be of order a few. And that's an interesting period for us, because that's also, gives us the number of events that can be localized within 5 square degrees to a few, which means it allows us the opportunity to make electromagnetic counterparts within that class. But beyond that, around 2019, when advanced LIGO reaches its design sensitivity, we expect tens of events at median expected event rate. Beyond advanced detectors, there is a need to go because there is a big frequency region that's completely unexplored and not reachable by current detectors, mainly because there is what is called gravity gradient noise. And in order to surpass that, I have shown here the future design, which still can't go beyond about 10 hertz. In order to surpass that, you need to go underground. And during 3 years, from 2008 to 2011, European Council funded a design study which resulted in this particular design of an underground triangular shaped interferometer. And this would consist of 2 interferometers in every V. You can see a green and a red here, a blue and a red, etc., which means 2 interferometers in each of these arms, V's. And that will lead to a sensitivity, which is, this is the sensitivity of the advanced detectors, but Einstein telescope will improve both in frequency as well as in strength. And that means that we will have a number of different sources that will be accessible to us and to very high redshift. This slide here shows you how, as a function of observed mass, Einstein telescope can see to redshifts of 17 and beyond. And if see black holes are truly stellar mass black holes, like 10 and 20 solar mass black holes, which we see in our own galaxy, we should see their mergers all the way to the edge of the universe. Now, what can we, these are my final 2 or 3 slides. What do we expect to learn from observing binary black holes? There are plenty. And I have listed only a sample, and I'm not even describing them in great detail. We can address questions in astrophysics, such as how do compact binary stars form and evolve. And this is a big theme in astrophysics, and the parameter space for astronomers is very high, and gravitational wave observations can constrain them. Is there a mass gap between neutron stars and astrophysical black holes? What is the spin distribution of stellar mass black holes? do intermediate mass black holes exist, and so on and so forth. Black holes in cosmology is bound to make a very big impact because gravitational waves are calibration-free standard cycles. So we can measure redshift by electromagnetic observations and distance by gravitational wave observation, and there's a great synergy between these two. Black hole seeds, as I mentioned already, are very important, and we can also hope to learn about anisotropic cosmology in other models. Finally, black holes and fundamental physics. Properties of gravitational waves can be explored because these signals could be extremely strong in our band. We can test generativity beyond the quantum pole formula. We can understand whether or not there are other polarizations than just the plus and cross, and whether gravitational waves have speeds equal to speed of light. Most importantly, we can test the no-hay theorem and cosmic censorship and really ask whether black holes of nature are really Kerr black holes. And that can come from observing the quasi-normal modes, which are the true signature of black holes. Thanks very much for this opportunity to talk in honor of Dr. Kerr. Thank you.